In this video, we will explore the Planck's model and its consequences. As we said in a previous video, a blackbody is an object that perfectly emits electromagnetic radiation. Also, we mentioned that any hot body can be thought as a black body. Up to a certain extent. In this sense, a correct description of the origin of the black body radiation was necessary in order to elucidate one of the most intriguing phenomena in the physics of 19th century. This is the black body radiation spectrum. An important model was developed by Baron Rayleigh and James Jeans. These well-recognized scientists used the known principles of classical physics to describe the black body radiation. This model is known as the Rayleigh-Jeans model. Unfortunately, this model worked only for the long wavelengths regime, but broke down in the near-infrared, visible, and UV range. Actually, this model predicted an infinite amount of energy to be released by a hot body in the UV regime. Due to this physical impossibility, this prediction was called the UV catastrophe. Let's think of the consequences of the UV catastrophe. Imagine that you want to bake a birthday cake. Then, you mix all the ingredients up and need to bake it. However, as the Rayleigh-Jeans model states, when you heat the oven, it should generate a huge amount of UV energy that could result in a fatal amount of radiation for any human. All this happening for temperatures of the order of hundreds of Kelvin degrees, a relative low temperature. Then, if we think of the temperature at the surface of a star, then the sun should be a source of an infinite amount of X and gamma rays, avoiding the existence of life on Earth, at least as we know it. It is clear that this model cannot be a correct one, as the experimental results showed a finite intensity in the black body radiation spectrum. Still, a correct model was necessary. One of the most successful scientists of the 19th century was Max Planck. He was an expert on thermodynamics and statistical mechanics. And at the end of the century, he centered his research on the black body radiation spectrum. He used the classical physics to determine the origin of the black body radiation. He had a weird idea, at least on his own beliefs, that got the correct model. Planck supposed that the interaction between light and the inner walls of the black body was held in integer numbers of a constant, instead of continuous as classical physics stated. Interestingly, Max Planck proposed the former only as a mathematical trick. His model successfully matched the experimental results and showed that the radiation spectrum only depends on the temperature of the body. But more important was the fact that the interactions in a cavity were quantized. This was a counterintuitive result, as all the interactions were considered continuous in the classical physics. Planck's model of the black body radiation spectrum has the following form. This form is in terms of the frequency. Let's take a moment to analyze this equation. It has the form of a distribution, similar to the Maxwell-Boltzmann distribution, as it was set in the same basis of entropy definition. Actually, Planck's model sometimes is referred as Planck distribution. Moreover, if we observe the argument in the exponential function, we can see that the term k times t has units of energy, where k is the Boltzmann constant, and t, the temperature of the system. This means that the product of h times f also has units of energy, with h a constant, and f, the frequency. The last means that the energy of the system is simply the product of a constant times the frequency. This equation generated the greatest revolution in the human knowledge. It set the beginning of the quantum theory that we will discuss in later videos. It is interesting to know that Max Planck was not convinced of his own discovery, and spent many years trying to prove himself wrong. Fortunately, he could not achieve this last goal. Summarizing, Max Planck discovered the quantization of energy in 1900. One of the most important tasks was to prove that Planck's model was correct. Then, the spectral analysis of sunlight was an easy-to-do activity. In this graph, it is clear how the Planck's model adjusts finely to the experimental data. However, it is very important to note that the model does not reproduces perfectly the experiment, as randomness of experimental conditions are not considered in the theoretical model. As we saw before, the Planck's model was written in terms of frequency, but it can also be expressed in terms of the wavelength, as follows. Next, Planck's equation proved that the Wien's and Stefan's laws could be deducted from it, without limitation in the electromagnetic spectrum. Finally, we can say that the Planck's model was a complete theory, and proved to be one of the pillars of modern physics. Let's solve an example regarding the Planck's equation. Example 9. Deduct the Wien's law from the Planck's equation. Could you solve it? Answer. We know that the Planck's equation, in terms of wavelength, is the following. We know that the Wien's law expresses the wavelength at which the intensity is maximum, then we need to maximize the equation as follows. In order to avoid messy operations, we define beta and x as follows. Then, the intensity has the following form. As we said before, we need to calculate the maximum of the intensity, then. That can be written as follows. After some algebraic manipulation, we get. Here, we have to note that the values of h, c, and k are constants. Also, the quotient of h times c and k is always much larger than the wavelength, expressed in meters, then we have. Finally, we get the following. Actually, inserting all the constants, we recover the Wien's law. Note how we have talked about the constant h in the Planck's equation, but did not define. This constant has proven to be a universal value, and probably one of the most important in physics. It is referred as the Planck's constant after Max Planck, and has a value of 6.622 times 10 to the minus 34 joules times seconds. We can see that the Planck's constant has a very small value. This is important to remember, as this means that the smallest amount of energy carried by a system is tiny, but never zero, as assumed in classical mechanics. Finally, it is important to notice that Max Planck was awarded the Nobel Prize of Physics in 1918 for the discovery of the quantization of energy. In the next video, we will explore another important discovery allowed by Planck's model. Stay tuned.